So we've been talking recently about the idea of the chemical formula and how the chemical formula tells us how many atoms of each element are in a particular compound. Now we want to talk a little bit about how it is we might determine what that formula would be. Okay? So for instance, we can undergo or make a molecule or a compound undergo a particular process called combustion analysis. In combustion analysis, we can then determine what the percentage of different elements are. Sometimes you'll hear that called elemental analysis as well. Depends on what technique is used. But what you get out of the process are the percentage of each element that are in that compound. Now in this problem it talks about vitamin C, and it says vitamin C is 40.92% carbon and 4.58% hydrogen, and then the balance is oxygen. You might say, okay, well I know how much carbon, I know what percentage of hydrogen, how much oxygen is there? And in reality, balance is just another way of saying the rest, the remainder. So if 40.92% is carbon and 4.58% are hydrogen, then all the rest, if you take those percentages and subtract them from 100, the rest would be oxygen. So in this case, 40.92% carbon and 4.58% hydrogen. That means there would be 54.50% oxygen. I just subtracted the known percentages right from 100. So it's saying, what is the empirical formula? So empirical formula is what we're going to call the simplest whole number ratio of atoms in a compound. This is not necessarily the molecular formula. It's not necessarily what the formula of the compound will be, but it's the simplest ratio of atoms in that compound. And you're going to see we're going to be able to figure out what the molecular formula is from the empirical formula, and that's not going to be a very difficult step for us to calculate, or a thing for us to calculate. So let's start in this problem. The way I like to do problems like this, and I do them very much like any textbook or any other professor or teacher would do them, is I break each element up into its own little row. So I'm going to have a row for carbon, a row for hydrogen, a row for oxygen, and these problems are going to be so methodical. If you can figure out the method on these, you'll be able to calculate all of them. And so in this particular problem, we know that we have 40.92% carbon. And so what we're going to do, because we don't really work with percent, we're good with grams if we're going to figure out moles and things like that. So if we want the simplest whole number ratio, or the simplest whole number molar ratio of atoms in a compound, we want to work with grams and moles. We don't want to work with percent. So we need to convert that percent into grams somehow, and we're going to do that by assuming, we're making the assumption that we have $100 grams total. Remember, percent is part out of 100. So if I have 40.92% and I have 100 grams, that means I would have 40.92 grams of carbon. And it means that I would have 4.58 grams of hydrogen. And it means that I would have 54.50 grams of oxygen. Okay. So the next step is that we're going to have to figure out how many moles of each of these elements that we have in our compound. So all that we're going to do is we're going to convert them to moles. And remember that we're elements right now, so all we're going to do is use the atomic mass. So there are 12.01 grams of carbon in 1 mole of carbon. And in hydrogen, there are 1.10, did it backwards, 1.01 grams of hydrogen in 1 mole of hydrogen. Those little things like transposing numbers and stuff, they happen to us too, even though we've done these problems over and over again. And I mean, it's in the thousands, if not tens of thousands of times I've looked at that atomic mass or thought of it. And I still got it backwards this time. So that does happen from time to time. Oxygen, there are 16.00 grams of oxygen in 1 mole of oxygen. So to do that, I'm going to go through and calculate, and I get 3.407 moles of carbon, and I end up with 4.535 moles of hydrogen, and end up with 3.406 moles of oxygen. Now I want the simplest whole number ratio between the moles of elements in the compound. That's what that formula is. It's a molar ratio. So to do that, the simplest way to do that is to take everything and divide it by the smallest number of moles. That way we ensure that at least one of them is going to end up as 1. So there's going to be so many moles of hydrogen atoms per mole of oxygen. And the reason why I chose oxygen is because oxygen is the smallest of the 3. So 3.406 divide by 3.406 divide by 3.406. And you're going to end up with something that's pretty darn close to 1 for oxygen and for carbon. For hydrogen, it will end up as 1.33. And you might say to yourself, okay, that is not a whole number. And you would be absolutely right. That would be a great observation. And in fact, we're not done, because we want to know what the simplest whole number ratio is. So we want these numbers to all be whole numbers. So we're going to have to figure out what can we multiply all 3 of these by to make them all a whole number. And in reality, it doesn't matter what whole number we multiply by 1, it's going to end up as a whole number. So we're not going to have to worry about carbon, and we're not going to have to worry about oxygen. The bad guy here is the hydrogen. And so we've got to figure out what can we multiply this by to end up with a whole number. And remember, if you think of a third, okay, a third is in fraction form 0.333. There are 3/3 in 1. Okay, so if I would take this and I'd multiply it by 3, because this is 1 1/3, and I'd multiply that by 3, you should get 4, or something pretty close to it. Now you have to be careful, all right? Because what you're going to find is this is not exactly 1, but it's really, really close to it. This is not 1. It's actually quite far from it. It's 0.3 away. And so you have to be careful. If this came out to be 1.1, you might round that down to 1. But I don't think I'd ever round 1.2 or 1.3 down to 1. So there are times where these are going to be so close to whole numbers that they're going to round right to the whole number that you might want or expect, or that it should be. But you have to be a little bit careful by looking at them, and you have to make a judgment. You have to say, okay, this number it's this fraction here, the decimal part is too big for me to really be able to round it. That is more than just 1. I mean, significantly more. So you have to be a little bit careful with that. But I multiplied that by 3 to give us a whole number of 4. Now I've got to multiply everything by that 3 to end up with 3, 4, and 3. So if we're looking for the empirical formula, we would have 3 carbon atoms. We would have 4 hydrogen atoms. And we would have 3 oxygen atoms. Now, another way to say this would be that we would have 3 moles of carbon atoms and 4 moles of hydrogen atoms and 3 moles of oxygen atoms. So a different way to say it, because these really are molar ratios of atoms in a compound. We're going to find with covalent compounds, generally, those are the number of atoms that are in the compound. But there are going to be some exceptions to that. And what we need to understand is that in both cases, those are molar ratios. So now, we've got the empirical formula. It's right there. Okay? Is that the actual formula for vitamin C? Well, that's where we're going to pick up in the next video.